Hello everyone, myself Rahul Thakur from M.TECH first year going to present a PowerPoint presentation on ultrasound as a food processing and preservation aid under the guidance of Dr. Charulata Mahanta. So pardon for any unwanted sound, there is a construction work going on beside my home. So I hope this presentation will explore your knowledge in ultrasound processing. So let's begin with the introduction. So ultrasound is a form of energy generated by sound which is really pressure waves of frequency that are too high to be detected by human ears, such that above 20 kilohertz. Depending on the frequency used and the sound wave amplitude applied, a number of physical, chemical and biochemical effects can be observed which enable a variety of applications like industrial applications, in food compositions or to enhance quality because it's non-destructive to the tissues. It's cheap, simple and energy saving because obviously it's non-thermal. So it's an emerging technology for probing and modifying food products. There are two types of ultrasounds. First one is low power or high frequency, and second one is high power low frequency. So in low power, its frequency is higher than 100 kilohertz at intensity below 1 watt per centimeter square, and it's monitoring the composition and physicochemical properties. It's non-destructive analytical methods, and its principle based on velocity, attenuation coefficient, and acoustic impedance. Attenuation is a reduction in force or pressure through a medium. And in high power, its frequency is from 20 to 100 kilohertz at intensities higher than 1 watt per centimeter square. It induces physical and chemical biochemical changes through cavitation. We will further discuss about cavitation in next slides, which supports many food processing operations such as extraction, freezing, drying, emulsification. And its principle depends on energy, intensity, pressure, velocity, and temperature. So the principle of low power ultrasound is given here. The ultrasound velocity is determined by density, elasticity E of the medium according to the Newton-Laplace equation. Here is it's the equation, and attenuation and acoustic impedance are expressed as here. You can see it. So A naught is the initial unattenuated amplitude of the wave, and X is the distance traveled, and R is the ratio of amplitude of reflected wave AT to the incident wave AT reflectance coefficient. Z1 and Z2 is equal to R, the acoustic impedance of two materials. So here is given the figure in which you can see that the reflection and transmission of an ultrasonic waves from the boundary between two materials. And here is the principle of high power ultrasound. So here's given the equation. PA is the acoustic pressure, a sinusoidal wave actually, which is dependent on time, frequency, and the maximum pressure amplitude of the wave. PA max is related to the power input or intensity I of the transducer. Here's the given the equation. You can say it, and where rho is the density of medium and v is sound velocity in the medium. So how ultrasound is generated? So ultrasonic waves producing system consists of three systems: generator, transducer, and application system. So in generator produce electricity or mechanical energy. Transducer converts this energy into the sound energy at ultrasonic frequency. Three main type of transducer are reported as fluid-driven, magneto-destructive, and piezoelectric transducer. Application system, a coupler device is used to transfer ultrasonic vibration to the sample. Here we come in sonication process. During the sonication process, longitudinal waves are created when a sonic wave meets a medium, thereby creating a region of alternating compression and expansion. Ultrasound on propagation through a medium induce compression and depression of medium particles. These regions of pressure change cause cavitation to occur, and gas bubbles are formed in the medium. These bubbles have a larger surface area during the expansion cycle, which increases the diffusion, causing the bubble to expand. A point is reached where the ultrasonic energy provided is not sufficient to retain the vapor pressure in the bubble. Therefore, a rapid condensation is occur. The condensed molecule collide violently, create shock waves. These shock waves create region of high temperature and pressure reaching up to 5500 degrees centigrade and 50 megapascal, and finally collapse. Cavitation can result in the occurrence of microstreaming, which is able to enhance heat and mass transfer. Cavitation depends on ultrasound characteristics such as frequency and intensity, product properties like viscosity, surface tension, and ambient conditions like temperature and pressure. The ultrasound intensity requires to cause cavitation increases markedly above about 100 kilohertz. This is the pictorial view of mechanism of cavitation. Here you can see that when the ultrasound is applied on the molecule, so here is the cavitation occurs. And the ultrasound applications. Method of ultrasound application can be divided into three: direct applications, coupling with the device, submergence in an ultrasonic bath. Ultrasound measurement techniques. There are four techniques: pulse echo techniques, continuous wave techniques, pitch and catch techniques, processes, tomography, and ultrasound imaging. This is the pictorial view of pulse echo techniques. It is the oscilloscope which measure the time delay in between the two frequencies, and this is the pulse. This is the pulse generator, and this is the sample cell, which may be our tissue or something. And this is continuous wave technique. There is the pulse generator, and it's a different type of oscilloscopes. So you can see it the schematic diagram of ultrasonic velocity continuous wave technique, and it's the method of ultrasonic velocity v calculation, delta t time delay also. This is pitch catch technique. Here we send the signal from here, and we receive the signal from here actually. So in this system, the pitch will be reflected from the uh, material being evaluated. The ultrasound imaging. UST pipe sensor, you can see it. It's the electrical cabinet in which, and we see the image and trends in the of our computer screen. And methods of ultrasound. Ultrasound can be used for food preservation in combination with other treatments by improving its inactivation efficacy. First one is ultrasonication. Application of ultrasound at low temperature for heat sensitive products. It requires long treatment time. Rise in temperature depend on ultrasonic power and time of application and need control to optimize the process. Thermosonication, combined method of ultrasound and heat, produces greater effect on inactivation of microorganism than heat alone when used for pasteurization or sterilization purpose. Lower process temperature and processing time are required to achieve the same lethality values as with conventional process. Method of ultrasound continued. Uh, Third one is manosonication. Combined method of ultrasound and pressure. It inactivates enzyme and or microorganism by combining ultrasound with moderate pressure at low temperature. It inactivation efficiency is higher. And manothermosonications, combined method of heat, ultrasound, and pressure, all three. It inactivates several enzymes at low temperature and or in a shorter time than thermal treatment at the same temperature. Applied temperature and pressure maximizes the cavitations or bubble implosion in the media, which increase the level of inactivation. It's thermoresistant enzyme, thermotolerant microorganism. It work on this also in these enzymes also. So there are several applications of ultrasound in food processing. You can see it. Uh, we will discuss one by one all this. So let's begin with the online measurement. The rapid and reliable measurement be non-invasive and non-destructive, be robust, low cost, easily automated and hygienic. Ultrasonic transducer set into the wall of the pipe through which the sample flows. The time taken for a pulse to travel across the sample T is measured using a digital timing device, and ultrasonic velocity is calculated for a knowledge of inside diameter of the pipe. So you can see the picture attached here. Determination of composition and microstructure. Application of ultrasound relies on there being a significant change in ultrasonic the properties of a material as its composition changes. The accuracy of the Mm, Ultrasound depends on how accurately the velocity can be measured. The magnitude of the change in velocity with composition, the greater the change and the more accurately the concentration can be determined. Measurements of the ultrasonic velocity and attenuation as a function of frequency are used to determine the particle size distribution. You can see the graph here between ultrasonic velocity versus glucose concentration. As we increase the ultrasonic velocity, the glucose concentration is also increasing, and we can check out perfect concentration of glucose in higher ultrasonic velocity. Foreign body detection. If an ultrasonic pulse is propagated into a sample, it will be reflected from any boundaries it encounters, providing there is a large enough difference in the acoustic impedance between the food and the foreign body, which is usually in the case. Most of the cases it happens that the foreign body have different acoustic impedance than food. The distance of the foreign body from the surface of the can is determined by measuring the time of flight. Means time of flight is the travel of frequency of ultrasonic pulses reflected from the foreign body and from the can wall. Here you can see the schematic diagram of it. Uh, Thickness and level detection. An ultrasonic transducer is pressed against the side of the material, and the time taken for a pulse to travel across the material and back is measured. If the velocity of ultrasound in the material is known, then you can see here the ultrasonic pulse echo technique for determining the thickness of the layer in multiple materials. Defoaming. The ultrasonic transducer creates a complex movement and covers a large deforming area at different rotation speed. Most of the bubble breaks almost instantaneously under the acoustic beam. Foam dispersion of gas in liquid with a density approaching that of the gas. Distances between the individual bubbles are very small, prevent decay and oxidation. Mechanical breakers which coarse forms, chemical antifoams decrease in surface tension, heat stresses rupture bubbles, heat intensity, ultrasonic waves. 80% of foam reduction have replaced aerodynamics acoustic source like siren whistles contamination prone. Here you can see the diagram of ultrasonic transducer for defoaming. Degassing and de-aeration. A liquid contains gases as a mixed condition. Common method: boiling and reducing pressure. Ultrasound or small temperature change. Rapid vibration of gas bubbles bring them together by acoustic wave, and bubble grows to size sufficient to large to allow them to rise up through the liquid against gravity until they reach the surface. So, what the purpose? To displace the air from the liquid surface in order to avoid organoleptic damage of the product by bacteria and oxygen. So, its frequency is from 20 to 50 kilohertz in low power ultrasound. Tea gas carbonated beverages such as beer, defoaming before bottling. Compared with mechanical agitation, the ultrasonic method decreases the number of broken bottles and overflow of the beverages. Polymerization. Degradation of polymers. Two possible mechanisms: mechanical degradation of polymer from collapsed cavitation bubble, chemical degradation as a result of chemical reaction between the polymer and high energy molecules such as hydroxyl radicals produced from cavitation. Sonication can lead to the several improvements in various properties, increased solubility and foaming ability. The application of low power ultrasound causes a temporary change, however, high powers cause depolymerization and result in permanent change in their rheology. In cooking, in a conventional cooking method, outside may be overcooked with the interior insufficient cooking. We can see a lot of times that outside is overcooked and inside the food is insufficiently cooked. The ultrasound improves heat transfer characteristic. Ultrasound cooking results in greater cooking speed, moisture retention, and energy efficiency. May improve the textural attributes of cooked meat. Mussels have 2 to 5 times less cooking losses than those cooked by boiling and convection. Demolding and extrusion. The device for demolding industrial food products couples the mold and the ultrasonic source in order to enhance removal of the product by virtue of high frequency relative movement between the contact surface of the mold and of the product contained in the latter. This technique allows surface coatings to be eliminated and ensure that any residual material in the mold can be cleaned automatically. Ease of removal makes the cleaning and recycle of the containers far easier. In cutting, ultrasonic cutting uses a knife-type blade attached through a shaft to an ultrasonic source. The most widespread application of ultrasound is in the cutting of fragile and heterogeneous products like cakes, pastries, and bakery products, and fatty, which is cheesy or sticky products. The vibration prevents the adherence of the product on the blade and thus reduces the development of microorganisms on the surface, such that ultrasonic vibration provide auto cleaning of the blade. The accuracy and repetitiveness of the cut produce a reduction in losses relative to the cutting due to cracks, crumbs, etc., and a better standardization of the weight and dimensions of portions. In freezing, under the influence of ultrasound, the conventional cooling provides much more rapid and even seeding, which leads to a much shorter dwell time. Sonication enhances both the nucleation rates and rate of crystal growth by producing a large number of nucleation sites in medium throughout the ultrasonic exposure. Cavitation bubble act as nucleation for crystal growth or disruption of seeds or crystal already present within the medium increase the number of nucleation sites. Of course, when the nucleation sites will increase, the freezing will be faster. Under the influence of ultrasound, conventional cooling provides much more rapid and even seeding, which leads to much shorter dwell time. Number of seeds is greater, and the final size of the ice crystal is smaller, and so cell damage is reduced. Defrosting and thawing. Use of acoustic energy for thawing frozen foods reported has many negative aspects such as poor penetration, localized heating, and high power requirement. Varying ultrasound parameters such as frequency and power. Overheating occur near the surface of the frozen food at high intensity as well as at a high and low frequency. Overcome this problem by adjusting frequency 500 kHz and intensity 0.5 watt per centimeter square for frozen beef, pork, and cod, which were thawed to depth of 7.6 centimeter within about 1 to 2.5 hour. Drying. A high power ultrasound improves heat and mass transfer phenomena in drying process. Acoustic dehydration relies on cavitation and also on the effect of compression and expansion induced by sound waves passing through the food medium. The dehydration of vegetable using forced area drying assisted by airborne ultrasound and ultrasonic dehydration has been carefully studied by the power ultrasonic group of the Institute of Acoustic in Spain. They designed a multi-sample ultrasonic dehydration prototype system which with a high power rectangular plate transducer which is 20 kilohertz or 100 watt and a series of sensors to study mechanical and thermal effects on vegetable samples and to evaluate the feasibility of the industrial level. In brining, pickling, and marinating, most current salt brining and pickling fermentation processes are subject to three main drawbacks. In brining, a very high sodium chloride content is required. The second one is there is a potential lack of control in fermentation. Third one, any soaking process can lead to enzymatic softening, structural damage, and blotting. So all three of these side effects are detrimental to rapid and efficient food preservation, and so alternatively technologies are of interest to food production. Ultrasound allows the pickling time of products to be reduced considerably, particularly those foods which are crunchy texture. It allows provide a method for manufacturing a pickle having low level of sodium chloride compared with the pickles currently on the market. Hence, there is no need to dissolve, repack to reach the desired finished product salt level. In sterilization and pasteurization, so in combination with heat, ultrasound can accelerate the rate of sterilization of food, thus lessening both the duration and intensity of the thermal treatment and the resultant damage. The advantage of ultrasound over heat pasteurization include minimize of flavor loss, which enhance the quality, greater homogeneity of treatment, and significant energy saving. Effectiveness have also shown the inactivation of enzymes such as pectin methylase polyphenol oxidase, and peroxidase, responsible for deterioration of fruit and vegetable juice, and various enzymes pertinent to milk quality. In emulsification and homogenization, the process requires an energy input by means of mechanical agitation or ultrasonication to facilitate the formation of small droplets. With ultrasonication, the collapse of cavitation release and from high energy microjets near interface and facilitate emulsification. Compared to mechanical agitation, the use of ultrasound requires less amount of surfactants and produce smaller and more stable droplets. Increased ultrasonic power increases the depressed phase volume and decreases droplet size. These effects were strongly dependent on viscosity of the oil and interfacial tension. In sonocrystallization, power ultrasound influences the crystallization of liquids and melt, such as sonocrystallization, increases nucleation rate due to high pressure pulse associated with collapsing cavitation bubbles, and modifies their polymorphic crystallization. Ultrasound modifies the microstructure, texture, and melting behavior. Power ultrasound induces primary and secondary nucleation, which yields small crystals and increase hardness. This effect could be tuned by controlling sonication time, power duration of the acoustic pulse, and crystallization temperature. Ultrasound assisted extraction. A major application of high power ultrasound is for facilitating the extraction process of a variety of food components such that herbal oil, proteins, polysaccharides, as well as bioactive ingredients such that antioxidants from plant and any animal resources. The action of HPU is due to cavitation, which generates high shear force and microbubbles that enhance surface erosion, fragmentation, and mass transfer, resulting in high yield of extracted materials and fast rate of extraction. The three major advantages of ultrasounds are minimum effect on extractable material, avoidance of ultrasonic solvent, reduction in extraction time, which can potentially enhance the extraction of heat sensitive bioactive components. Now, applications on food preservation. So, directly related to food, microbial inactivation, enzyme inactivation, are indirectly related to food surface decontamination. So, let's discuss about it. So, in microbial inactivation, thermal treatment often leads to unwanted flavor and loss of nutrients. Type of bacteria is an important criteria that changes the effectiveness of an ultrasound treatment. Factors affecting the effectiveness of microbial inactivations are amplitude of ultrasound waves, exposure or contact time, volume of food processed, composition of food, treatment temperature. So this is the flow diagram of process. So first one is continuous vibration, second one is cavitation bubbles, then collapse, and then breakdown of cell walls, disruption and thinning of cell membranes, and DNA damage via free radical production. Next one is spore inactivation. Ultrasound alone is ineffective against spore. Combining the effect of a 20 kHz ultrasound probe on sample under static pressure indicated an increase in static pressure and resulted in an increased level of spore inactivation. Manosonication, we have discussed already. Treatment at 500 kilopascal for 12 minutes has been seen to inactivate over 99% of the spores, which is quite high, increasing the amplitude of ultrasonic vibration of the transducer such that the acoustic power entering the system increase the level of inactivation. Finally, the increasing the thermal temperature of the treatment results in greater rates of inactivation compared to thermal treatment alone. So, now in enzyme activation, this flow diagram is somewhat disturbed. Uh, Enzyme inactivation. Heat treatment to eliminate enzymes is the commonly used method, but it is also destroyed nutrients and may cause loss of food quality. Ultrasound is an effective method in the inactivation of enzyme like glucose oxidase, in peroxidase, pectin methylesterase, protease, and lipase, and polyphenol when it is used alone with temperature and pressure. So this is the flow diagram of enzyme activation. Like this is continuous vibration, then we give cavitation bubbles, and it may go through homoelectric water molecules cleavage generating free radical and free radical amino acid plus some residues. and here it's may collapse and modification of secondary and tertiary structure of protein. So surface decontamination. Objects that can be cleaned range from large crates used for food packaging and transportation to plastic baskets, shackles, the hook used for hanging a poultry and a production line, which is shackles means this, and conveyor belts. Crevices are easily cleaned that are not easily reached by conventional. The acoustic cavitation phenomenon, the formation, growth, and implosive collapse of cavities, which is gas bubbles in liquid that release high amount of highly localized energy. The collapse of cavitation bubbles near solid surface forms asymmetric microjets, which cleanse surface from contaminants. Effect of ultrasound on food quality. Ultrasound is reported to have a minimal effect on the quality of fruit juices such as orange juice, guava juice, blackberry juice, and strawberry juice. And fruit juice color is also preserved. Various color measurement during storage of fruit juice have after heat or ultrasound treatment indicate similar overall changes, but significantly lighter products resulting from the ultrasound treatment. So advantages: inexpensive to purchase and operate, rapid, less than 1 second, and reliable measurement in a non-destructive and non-invasive manner. Measurement can easily be automated, and so the technique is suitable for online measurement as well as an analytical instrument in the laboratory. Limitation: only a few commercial instruments specifically have been designed for application to food materials at present. The technique is fairly application specific, so that calibration experiments have to be carried out. Sorry, carried out for each new application. Ultrasound is highly attenuated by materials which contain small air bubbles, which may limit its application to certain food. Now we come to the concluding the remarks. We have discussed about emerging technology, diversified applications, portability and low cost, low power ultrasound, high power ultrasound, and ultrasound is a green technology. So here's the reference. You can check out this paper. So guys, this is my presentation. If you have any query, comment your questions in comment section with your email ID. I will try my best to answer you. Thank you. Have a good day.